Hello. So what we're going to be talking about right now is we're going to continue talking about definite integrals and how they apply to area. So instead of now having to find a summation for a curve to find the area and just approximating the area, we're going to be able to use a definite integral to exactly find the amount of area that's under a curve. And then we're also going to talk about some properties of the definite integral, just like we talked about the properties for indefinite integrals, derivatives, limits, and all of that. Okay, so let's get started. So the area under a curve between points A and B is defined to actually just be the definite integral from A to B of f of x dx. Now there are specific caveats with that, which we're going to go over in a second. So if you ever want to find the exact amount of area under a curve, all you do is you take the definite integral between those 2 points. Pretty simple. And soon we're going to be learning new ways to evaluate those definite integrals so you don't have to do the summation and take the limit as n goes to infinity. So correctly interpreting area under a graph. So say I have just this general function, and I let this be my point A and this be my point B. And I want to find the area between A and B. So in other words, I want to find all of this area. Now, in the real world, we don't have negative area. But because we are in calculus and we have this function graphed over a coordinate plane, where we do have this area being below the x-axis, we actually have negative area in math. And it's just because the function values at this point of the curve are negative, so that when we multiply by the function values in those little widths of those rectangles, we actually get negative values. So we do have negative area in math. So if we first define this point here in the middle where they cross from positive to negative y values, let's let that be point C. So what we're going to do now is we're going to label this as A1 because we'll let it be our first amount of area, and A2. So the total amount of area from A to B that's really going to be A1 minus A2. And that's simply because A2 is negative. So to counteract the negative sign on that and get the total amount of area, we need to subtract it out. So in order to do that with integrals, what we're going to do is we're going to do the integral from A to C of f of x dx, because that's going to give us our A1, minus the integral from C to B of f of x dx. So instead of just doing the integral from A to B of these two things, we're actually going to have two separate integrals and we're going to subtract them from each other in order to counteract the negative area of A2. And just for clarification, this is not going to equal the integral from A to B of f of x dx. If we were to do the problem both ways, just the straight integral from A to B and then splitting it up and doing the subtraction of the two integrals, we'd actually see that we get two different numbers. So that's how you would correctly interpret area under the graph. So you want to find the area of each individual piece and then add them all together so you get a positive number at the end. Okay, so we're going to find the area under the curve for 4x minus x squared between 0 and 4. And we're going to use the limit definition of the definite integral, just like we were before, since we haven't actually learned a new way to do it yet. So we're going to quick graph it. So at 0, if we plug in for 0, we get 0. And if we plug in for 4, we also get 0. So this is a parabola. So the vertex is going to be halfway between these 2 points. So the vertex is at 2. So we plug in 2, we're going to get 8 minus 4, which is 4. So we're going to find the area of this piece of the parabola. And then of course the parabola is kind of going down like this. But we're just going to focus on the area that's between 0 and 4. So we want to find the integral from 0 to 4 of 4x minus x squared dx. But we know that that's really just equal to the limit as n goes to infinity of the sum as I goes from 1 to n, And now we're going to, before we plug in, we're actually going to straight plug into the integral. So, or the sum rather. So we're going to do xi and delta x off to the side. So delta x is b minus a, which is 4 minus 0, so 4 over n. And a in this case is 0, so our xi is actually just going to be 4 over ni if we use the right-hand endpoints. So we're going to do 4 times 4 over ni minus 4 over ni squared, all times delta x, which is 4 over n. So now all we have to do is evaluate our summation and then take the limit. So first thing we're going to do is we're going to pull this 4 over n out front because it's a constant. We know we can do that. And then we're just going to separate this into two different sums on the inside and pull out any constants that we have then. So then we're going to get the sum of 1 to n. 4 times 4 over n is just 16 over ni minus the sum from I going from 1 to n. 4 over n squared is 16 over n squared times I squared. Okay, so then we could end up brackets, and now we're going to pull out those constants on the inside of the sums. So we're going to get 4 over n times 16 over n times the sum from 1 to n of I minus 16 over n squared, sum from 1 to n of I squared. So now we're just going to plug in and simplify. So we're going to take this over here so we have some more room to work with. So we're going to get the limit as n goes to infinity of our 4 over n times 16 over n. And then the sum from 1 to n of I, we're just going to plug in our regular formula then. So n times n plus 1 over 2 minus 16 over n squared. And then the formula for the sum of I squared is n times n plus 1 times 2n plus 1 all over 6, I believe. And now we're just going to simplify on the inside and take our limit. So this is why we want to really have those summation formulas memorized, because it makes solving these types of problems a lot easier. So we're going to have 4 over n. So in this first one right here, I'm going to simplify this first. So we have an n down here and an n down here. So I can cross both of them out. And then I can also cross cancel between my 16 and my 2 and make this an 8 up top. So what we're going to get is 8 times n plus 1 over 1 minus, now we're going to do the same sort of simplification over here. So I have an n up top and an n squared in the bottom, so I can reduce the power to just one n in the bottom. I can reduce my 6 to be a 3, and I can reduce my 16 to be an 8. So then what we're going to get is an 8 times n plus 1 times 2n plus 1 all over 3n. So now we're going to have the limit as n goes to infinity. And we're going to multiply in our 4 over n now. Whoops, forgot that n parenthesis there. So if we multiply this 4 over n into this first, we're going to get 32 times n plus 1 over n minus 32 times n plus 1 times 2n plus 1 over 3n squared. And so now we just want to take the limit as n goes to infinity. So when we take the limit as n goes to infinity, we want to consider those cases back when we're talking in 3.5 about horizontal asymptotes. So we want to compare the powers of the top and the bottom. So the highest power in the top, without even multiplying the first one out, is 1. because we're going to have one n here and one n here. And we don't have any other n's multiplying in the numerator. So because our powers in the top match, we know that this first one is just going to be a 32 over 1, because it's going to be the ratio of the coefficients, minus, so now the highest power in the top on the second one is going to be when we multiply n by 2n squared by 2n. So we're really going to have a 2n squared over 3n squared. And then we also have the 32. So what we can do is we can do plus 32 times the ratio of the coefficients of the highest power for here, which is going to be 2 over 3. And now all we have to do is simplify. So we're going to get 32 over 1 plus 64 over 3. So if we make these both into fractions over 3, we're going to get 96 plus 64 over 3, which is just going to be equal to, if we do the math off to the side real quick, 10 carry the 1, we're going to get 160 over 3. So that is the amount of area under the curve between 0 and 4 of 4x minus x squared. So that's how you would go about doing a problem like that. And like I said, soon you're going to be learning an easier and much quicker method to evaluate a definite integral. So you won't have to do all this summing and all the different math where there's a lot of room for error. So now what we're going to be talking about for the rest of the video is different properties of definite integrals. So the first thing that we're going to talk about is two special definite integrals. So the one is when we do the definite integral from a to a of f of x. Now if you think about that in terms of area, that would be finding the area under f of x from point A to point A. So in other words, you're just looking at a singular point on the function. So there's no area under a singular point because you have just one infinitesimal slice. So the area is going to be 0. So that's pretty easy to remember. And then the second one, this bottom one, is if you have originally the integral from b to a of f of x, if you flip the order of the limits on the integrand, so see over here we have b and a, but then they go a to b over here. So if you flip the order of the limits on the integral symbol, all you have to do is add a negative sign out front, and they're the same thing. So when you flip the integral limits over, you just have to add a negative sign to make your integrals equal to each other. Pretty basic property. So now we also have what's called an additive integral property. So if we have points, if we're taking the integral from a to b of f of x dx, we can split that into two different integrals and add them together through this point c that's between a and b. So for instance, if we were doing the integral from 0 to 2 of f of x dx, we could take that to be the integral from 0 to 1 of f of x dx and add that to the integral from 1 to 2 of f of x dx. So these two numbers always have to match each other, so that way when you could squish them together and get back from 0 to 2, which is why earlier when we were talking about how to correctly interpret area, notice that we had a minus sign in between them instead of a plus sign, which is why they weren't technically equal to the full integral from just a to b or anything like that. So you can always split up your integral and add them together, stuff like that. And then two more properties to go over. So now we have the properties of definite integrals. So we have our first one, which is the constant rule. So just like any other property that we've talked about with constants, if you have a constant on the inside of an integral, you can pull it to the outside and then evaluate the integral of just the function, and it'll be the same thing. Just like it was with limits and indefinite integrals and derivatives and all of that fun stuff, and sums and all of that. So then we have the summation rule. So we have sum and difference. And just like with derivatives, limits, sums, all of that, if you have the integral from a to b of f of x plus or minus g of x, you can split that up. You can distribute that integral sign to both functions and evaluate them individually. That's all it is. So now we're going to use all of these different properties to help us evaluate the integral from 1 to 3 of negative x squared plus 4x minus 3. And we're going to use those three different values on your screen to help us do that, since we don't know how to algebraically evaluate a definite integral yet. So 1 to 3 of negative x squared plus 4x minus 3 dx. We're just going to use the sum and difference rule first to split that integral up into 3 separate integrals. So we're going to get the integral of negative x squared dx from 1 to 3 plus the integral from 1 to 3 of 4x dx minus the integral from 1 to 3 of 3 dx. And so now what we're going to do is we're going to pull all of the constants out using our constant rule. So we're going to get negative integral from 1 to 3 of x squared dx plus 4 integral from 1 to 3 of x dx minus 3 times the integral from 1 to 3 of just dx. And now if you notice, all of these integrals match what we have up here. So now we're just going to plug in those numbers and simplify. So we're going to get negative 26 thirds plus 4 times 4 minus 3 times 2, which is just negative 26 thirds plus 16 minus 6, which is negative 26 over 3 plus 10, which is going to be negative 26 over 3 plus 30 over 3, which is going to be equal to positive 4 over 3. So that's one way that you could use integral properties if you're given those different values, to just split up your integral and plug in the different values that you're given in order to find the value of the whole definite integral. So now one more quick theorem before we go, and it's called the preservation of inequality theorem. And all it says is, the first part says if f of x is integrable, so if you can take the integral of f of x, and it's always positive on a to b. So in other words, your function from a to b is just positive. So it could even look like something like crazy like that. As long as it's above the x-axis between the interval and you know how to take the integral of it, then you know that the value of your definite integral is going to be larger than 0. It could be equal to 0, but it's definitely going to be greater than or equal to 0. And the second part of it says that if f and g, if you know how to take the integral of those on a to b, and f of x is always less than or equal to g of x. So say you have a function on a to b. So if f of x is something like this, and then we have g of x being something like, woo, like that, but it's always above f of x, then you know the integral from a to b of f is going to be less than or equal to the integral from a to b of g. That's all it's saying, is that if you know a function is always lower than another one, the value of the definite integral on the same interval will be lower than the definite integral of the larger function. So that's all the properties that I wanted to talk to you today about definite integrals. So I hope this helped. Have a great rest of your day.